This is a speedrun from July 2019, created by Mastergen and AIS 523. If you're wondering where the game is, then you probably blinked. The whole speedrun takes place in 78 milliseconds, or 47 frames, and it looks like nothing but a bunch of glitchy curtains. This is the current task world record in the Super Mario Bros. 3 Credits Warp category, beating out the last one by almost 3 minutes. Now, something about watching this speedrun for the first time ignited a spark of curiosity within me. I knew I had to figure out what made it all possible. Luckily, in the video description, there was a link to the task videos post with an explanation, but unluckily, even the explanation made no sense to me at the time. Well, 2 months and many hours later, I can finally say that I kinda sorta maybe understand what's happening. And since I hadn't seen an explanation video for this run yet, only a couple for the last world record, I thought I would try my hand at making this one, to save some people the trouble of having to find all the info themselves. I based this video off the task videos post, only I changed around the order a little bit and added some more background information, so that hopefully even people with little to no prior knowledge on this topic will come out being able to understand it. As with most credit warps, this one also relies on arbitrary code execution, ACE for short, to warp from a point in the game straight to the credits. ACE relies on manipulating the game to incorrectly read stored values in memory as code. Some stored values in memory can be player controlled, such as coordinates of sprites, player position, speed, etc. So by manipulating those values in-game, you're able to effectively write code for the game to execute. Usually some sort of game crash is required in order to get the game to this point, and in this run specifically, it's done by mashing a bunch of buttons really fast. Once the crash happens, the game jumps around in its code and lands on the part of the memory that stores controller inputs. From there, through a precise set of inputs, you can get the game to initiate the credits sequence, and bada bing bada boom, finish speedrun. It's just that simple. That's the gist of the speedrun. The rest of the video will be going more into depth on the how, starting with the very basics and building upon it all the way to the end. Each section will be timestamped in the description, so you can skip through any sections that you might already know. Let's start from the very beginning. Binary. Binary is a counting system in base 2, meaning that the only numbers you will ever see are 1s and 0s. Here's 0 in binary, here's 1, and that's as high as you can get with just one digit. Like in base 10, if you want to go higher, you'll start needing to add more digits. Here's 2, 3, 4, 5, and so on. In base 10, the value of each new digit added is 10 times the value of the previous digit, hence the name base 10. Therefore, in binary, each new digit is worth double the one before. So, in order to convert a number like this into base 10, all you have to do is add together the place value of all the digits that have a 1, resulting in 108. So why is this relevant? Well, all processors store things as bytes, each made of 8 bits, which can either be on, which is a 1, or off, which is a 0. Using 8 bits, you have a string of 8 digits in binary, giving you a counter that can go from 0 to 255 to store data in. But reading a string of 8 digits for each byte is a bit of a pain, so there's a more human-friendly form of notation known as hexadecimal. Hexadecimal is a different counting system in base 16, using numbers 0 to 9 and then the letters A through F. This is perfect for representing binary since 4 digits in binary go up to 16, meaning that hexadecimal can convert the 8 digits of a byte into 2 characters, saving a lot of space when you're trying to display a large quantity of bytes and generally making it easier to read. To convert from binary to hex, simply split the byte in half, and then write each half as the respective value in hex. Converting the previous number to hexadecimal gives you 6C. The most common way to display bytes is in hex, so hopefully the random numbers and letters that you see later on in this video will now mean something to you. As previously stated, data is stored in a processor as bytes, and controller inputs are no exception. It just so happens that an NES controller has exactly 8 buttons, which means that if you pair each button to a digit in a byte, you can store one input in one byte. The buttons are mapped to the bits in this order: A, B, select, start, up, down, left, and right. Here's some example inputs and their respective values. But not every byte is possible to store, since up and down or left and right will cancel each other out, so it's not possible to have any values that end in 3, 7, B, C, D, E, or F. Obviously, the NES needs more than just one byte for storing controller input, because games like Mario need to be able to tell if a button is being held and also for how long. Plus, you can never forget about player 2. In the RAM, a total of 6 bytes are used to store controller inputs. The addresses 17 and F7 are used to store current player 1 input, F8 for player 2 input, 18 and F5 for new player 1 input, and F6 for new player 2 input. If you're wondering what these addresses are, don't worry, I'll cover them in the next section. When a new button is pressed that wasn't pressed in the previous frame, these new buttons get stored in the new input byte. Note that new input bytes are not the same as currently held bytes, since the new byte only stores the bytes that have changed from unpressed to pressed. So that's cool and all, but how does a controller input translate into executable code? When you hear the word code, you might be thinking of something like lines of text written in a coding language like Java or Python. These are coding languages created to make things easier for humans to read, but computers don't need to be able to read to understand code, so they operate using a different coding language, one of which is called assembly. In assembly, code is written with hex values, and each hex value has a corresponding code instruction. Fully learning assembly is definitely not necessary to understand this run, and I didn't learn it either because it just seemed like way too much work. The reason why this is relevant though is that while hex values can be used to store data, the same hex values can also be used as code, which is exactly what happens during ACE. Normally, the stored values in RAM are used as values, but when moving the pointer into RAM, it'll start reading these stored values as code instead because the computer really doesn't know any better. I've mentioned RAM and memory a few times now, so let's finally address it. The NES has 65,536 bytes of storage, and each byte has a specific name known as its address. Addresses are denoted with a $sign and range in value from 0000 to FFFF. These addresses are divided into banks of various sizes, which are further divided into pages of 256 bytes each. 0000 to 00FF, for example, is the page where the controller input bytes are located, as stated in the previous section. For a more detailed look on how the memory in the NES is divided up, here is a CPU memory map. Some important sections to note here are the section from 0000 to 0200, which makes up the RAM, and the section 8000 and FFFF, which make up the various ROM banks. The ROM and the RAM are the parts of memory responsible for storing the game code and temporary values, but there's a small issue with NES ROM. The NES ROM is only 32 kilobytes big, which is really not a lot of space to store game code, especially not for a big game like SMB3. So NES game devs created a pretty clever workaround for this space issue called the mapper. The mapper is a thing responsible for swapping the ROM banks in the game cartridge into the ROM banks in an NES. Whenever the game needs a certain bit of code, it swaps the relevant cartridge bank into the NES banks, and then swaps it back out when it's no longer needed. This way, games way larger than 32 kilobytes can be made. Now that we have the required basic info, let's get into the first step of the ACE, crashing the game. There's a hardware bug inside the NES which can sometimes cause incorrect inputs to be read. This occurs when the system tries to do sound processing on the same cycle as it tries to read inputs, leading to a bit being deleted from the controller input byte. To fix this, the SMB3 devs created a workaround. By constantly checking the current input and only registering it when 2 consecutive checks match, they can be sure that the bug has not affected the current input that was registered into the game. This process happens somewhere around 8,000 times a second, so even the shortest tap by a human would take up at least a few hundred of them. However, TASes are not humans, and they aren't bound by the same limitations of flesh and muscle that we are, so a TAS is fully capable of changing the inputs every single check. The input checking is part of a process known as the NMI interrupt process, which runs at the start of every frame. This process stops the CPU code, swaps some ROM banks around, does some stuff with the new banks, input checking being part of it, and swaps the banks back. But because you're switching the inputs once per check, that part of the NMI is delayed since it keeps trying over and over to no avail, and eventually a second interrupt known as the IRQ starts up that was never meant to run alongside the NMI. The IRQ is expecting the NMI to have ended long ago and that the banks that were swapped out are now back where they should be. But because this hasn't happened yet, IRQ is now reading code off the wrong banks, leading to all sorts of interesting interactions. A couple of buggy jumps later, and the computer pointer is now made it into address 0000, which is the very start of RAM, ready to execute what it thinks is proper code. Here's the visualization of the first page of RAM, and here are the bytes that store controller inputs. At this point, the CPU pointer is sitting at the start of RAM and will start going up through all the memory addresses, executing the bytes in chunks. If nothing is done, eventually it'll increase past the first page of RAM and into bytes that can no longer be controlled. In order to stop this, the 4-byte chunk of controller input here needs to be used to save the bytes 20:00:00, which translates into a JSR, or jump to subroutine, instruction, sending the pointer back to 0000. Because of this, the only real bytes that can be used for other code are the 2 bytes here, which are responsible for P1 input and P1 new input respectively. Now remember that a large chunk of the possible bytes are also restricted due to opposite D-pad inputs being cancelled out, so the solution to this puzzle becomes a lot more difficult. But then again, what exactly is the puzzle that we're trying to solve here? There are a few requirements that need to be met in order for the credit sequence to properly play out, which are detailed here in the task videos post. However, the only real important ones are number 4 and 5, since the other ones work out automatically in most cases. 4 and 5 can be done separately, but the easier method is to simply JSR our way to address 8FE3, which is where the game jumps when you normally initiate the credits. It might sound simple, but there's all sorts of potential problems that can occur. Some of them are listed in the task videos post, but for the sake of simplicity, I chose to leave it out of the video. Finally, we can get to analyzing the actual run. Before we get into this section, I would like to preface it by saying that this is the part of the post and the video that I am the least confident about. As I stated earlier, I didn't actually learn assembly for this, so as a result, I might not fully understand some of the stuff that is happening. That being said, I've picked out what I think are the most important frames of the run, and I will explain them to the best of my ability. I will be using the visualization for Mastergen's video, so let me give a quick explanation of the layout. In each frame, the highlighted portions of the memory are the bytes that are executed. Alternating colors indicate how the bytes are grouped when executed. The first number represents the amount of times that the input check process in the NMI is delayed, which is sometimes required to give the game enough time to store values in the right bytes before the execution reaches them. Next up is player 1 and player 2 current held byte along with the buttons held in that frame. Along with the display, the X and Y registers are also referenced in some steps. You could think of registers as just another form of memory, which are easier to access since some instructions are able to read or write to them directly. Here, the address 14 is decreased by the value of X, from 00 to FF. FF is a 3-byte long instruction, so addresses 15 and 16 are never executed, which prevents potential problems in the future. Here, another FF is written to address 0F, allowing address 10 to be skipped over in the future as well. Here, FF is written to address 06, ensuring that all future loops are aligned properly in order to execute addresses 17 and 18 in one chunk. One final FF is written to address 3F to align the execution after it, so that it ensures it is always consistent. Here, the value 20 is stored into the X register. The value of 20 is now read from the X register and stored into address 86, forming an early looping point and saving the trouble of having to set up the 4-block byte each time. This also allows for storing values in the Y register now, by skipping execution of address 8D, which was resetting the Y register in each loop, freeing up yet another tool to work with. The value F9 is stored into the newly freed up Y register. The value 8F is stored into the X register. Using these two registers, the value 8F from X is written to address F9 from Y. The Y register is also used to write F9 to address 84. F9 is also a 3-byte instruction, so 86 is no longer executed and the loop that was set up earlier is now broken, allowing the pointer to once again reach the 4-byte block. These 3 bytes form the JSR 8F-E1 instruction, sending the pointer to 8F-E1, which will eventually reach 8F-E3 to roll credits. Huge thanks to Mastergen for being willing to help me out while I was doing the research for this video, and also a huge thanks to Bismuth and Retro Game Mechanic Explained for their videos on the previous method of credit swap, which also helped me out a ton. For those interested in doing further research, I'll link the resources that I use in the description of the video. If you stuck around all the way to the end, consider giving the video a thumbs up and maybe even subscribe if you're feeling really generous. Full disclaimer though, I really don't think I'll be doing this type of speedrun explanation content in the future, so if that's what you want, maybe consider going to Summoning Salt's channel instead. See you next time!